What's up, guys? So I have another example for you all. We're going to be solving the maximum bending stress in the beam with this triangular load. We have this rectangular cross section. We have a couple answer choices, and we're going to plow through this together. All right, you guys? So, yeah, let's do this. So, maximum bending stress. Our bending stress equation is sigma is equal to negative my over I. Negative my over I. Cool. So let's see what we know. So we have this rectangular cross section. So we know that for rectangles, we can just do 1 over 12 base times height cubed to find our moment of inertia. So let's just do that now. 1 over 12 base, which is 8 inches, height, which is 12 cubed. So that's 1152 inches to the fourth. So that will be our moment of inertia. Now, the question asks for maximum bending stress. And we know that maximum bending stress occurs at the extreme fibers, and we also know that the neutral axis for a rectangular cross section is in the middle. So we know that our y distance, if we're trying to get to the extreme fiber, should be 6 inches. So we know that y should be equal to 6 inches. Cool. So we have 2 out of the 3 variables we need to answer this question. It's pretty nice. So now what I will do now is I will try to solve for the moment and see where that takes us. Now, I'm gonna solve this in a unique way. Instead of doing bending, moment, and shear diagrams, I'll solve this by actually doing integration. I think personally that would be easier because this is a triangular distribution. Finding that the point at which the shear will be 0, and then taking the area under the curve is going to be difficult if we do the bending moment diagrams and the shear diagrams, and we may end up having to integrate anyways. So I think the best route is probably to just go ahead and integrate this from the start. So I'll show you how to do that. So I'll redraw our beam here. So we have this beam, we have this pin, this roller, we have this triangular distribution, and we have this. We have the 20 kips per foot, and we have the 12 feet. So first, we need to establish, in order to integrate this function, or in order to integrate this problem, we need to establish a function that will simulate what's going on here. So we have this line, and we need a function to simulate this line. So I usually call these Q. So Q of X should equal, and so here what I'm going to do is kind of make some mental notes here. So our function, if let's say it were to start where x starts and goes from this direction. If x is 0, so at x equals 0, the triangular distribution, the forces are 0. So Q of x should be 0. Now, at x equals 12 feet, Q of x should equal 20 kips per foot. So we need a function that is going to be able to produce this. So I think the easiest way to do this is to try, let's say, we divide the 20 by 12, so that way when we get to the 12 feet, we get the 20 kips per foot. So we can do that. 20 divided by 12 is equal to 1.67. So, and we're going to make this as a negative because, as you can see, this is a downward force. So we want to make sure we incorporate that. So I'm going to try this function and see if our conditions work. So negative 1.67 x. So let's see, when x equals 0 on our function, we get 0 in our triangular distribution, which is good. When x equals 12, we get 20 kips per foot, which is perfect. That's what we want. So let's integrate this function and see where it takes us. So one thing to note as well, when we're integrating a function, q of x, let's say, like we have here, when we integrate once, that's going to give us our shear. When we integrate that function twice, it's going to give us our moment. It's going to give us our moment distribution, our moment equation. Just a couple of things to keep a note, and ultimately, I'm trying to find that moment. So, as you can guess, we're gonna try to integrate this function twice. So, here we go. So, let's integrate this function to get the shear. So we integrate this function once. We're going to integrate with respect to dx. So we should be integrating negative 1.67 x dx. So if we integrate that, we're going to get negative 1.67 x squared over 2 plus c1. Remember, when we integrate, we always introduce a constant in our equation. So we have this equation now. Now this is our shear. What's true about our shear? So that's kind of what we need to figure out here. So what I should have started with in the beginning was finding our reactions, because that's going to give us information on our boundary conditions and hopefully help us find what the C value should be. So let's try to find the reactions here. So AY, BY. So the force on this triangle should be the area of that triangle. So 1/2 times the base, which is at 12 feet, times this 20 feet, or 20 kip per foot. That gives us a force of 120 kips. So now, if we take the moment about, let's take it about A, then we get this negative 20 wanting to rotate this way about point A. So we get that negative 120 times this distance, usually for triangles, this distance is 2/3 of the length from here to here. So 2/3 of that is going to be 9 feet. Sorry, I think 8 feet. Yep, that's 8 feet for that. So 8. And then we want to do plus by times the full 12 feet. And then so by should equal 80 feet, or 80 kips. That means ay should equal 40 kips. So we found our reactions. So that helps us a lot. So because we know that in our shear diagram, when we create it, we know that this AY reaction is going to shoot the shear reaction up to 40 kips. So for shear, we know at 0, at x equals 0, the shear is equal to 40 kips. We know that because we just proved that the reaction is going to shoot up at 40 kips at 0 feet. We can see that. So therefore, we can set our equation, this v of x that that we just solved for, the shear equation, if we were to do v of 0, then this term would go away, and we know v of 0 would be 40 kips. So we know that C1 is equal to 40 kips. Well, great. So now we know our full Vx equation is equal to negative 1.67 x squared over 2 plus 40. Cool. Now, if we integrate one more time, we're going to get our moment equation, which helps us a bunch because we need the moment to be able to solve for that bending stress, right? So let's integrate one more time and see what happens. So let's integrate this function, the v of x function that we have. We're going to integrate that negative 1.67 x squared over 2 plus 40. Let's integrate that, and that becomes negative 1.67 x cubed over 6 plus 40x plus c2, let's call it, a new constant of integration that we need to solve for. So now we have to think about, well, what do we know about the moment, right? Well, if we look back at our free body diagram that we have here with our reactions, our pin isn't really giving us any moment resistance there. So the moment is going to be 0 at that pin. Therefore, we also know that at x equals 0, the moment should be 0. So at x equals 0, moment of x, the moment is equal to 0 as well. So let's try that. So So we know the moment is equal to 0 when x is equal to 0. So this term goes to 0. This term goes to 0. So C2 must equal 0. So our final moment equation then is that negative 1.67 x cubed over 6 plus 40x. Because that constant of integration, it was actually 0 for that. So now that gives us our moment equation, but it doesn't really give us our maximum moment. But there is one thing we know about the relationship between the shear and the moment. So we know that when the shear is equal to 0, we know that when the shear is equal to 0, then this produces our max moment. So if we set our shear equation that we solved for up here, and set that equal to 0, and solve for the distance at which that 0 point happens, that would be very important for us, because then we could use that distance and find what that maximum moment could be, right? So let's try that. Let's try to find the x value that produces a 0 shear. That's basically what we're doing here. So I'm going to copy this equation since we need it again. The one we integrated the first time. And so basically we're saying if we set this equal to 0 and find that distance should be the distance that produces the max moment for our beam. So let's see. If we were to solve that, so let's see. If we solve that, we get x is equal to 6.92. And that's in feet. So that's basically saying at 6.92 feet, that's when the shear is 0. So then, well, if the shear is 0 at that point, then that will be the point where our maximum moment happens. So let's plug this one into the moment equation now. So I'm going to copy this moment equation. Let's use this one again. So moment about 6.92 is equal to, let's see what that equals to. If we plug 6.92 as x, times, let's see, like it says 184.6 kip feet. Great. So now we have a value, and this is equal to m max. Cool. So now we can go back in, solve for our max bending stress, because now we know our max moment. So now we know it's 184.6 kip feet. We want to make sure we convert that to inches. So we want to do that 1 foot over the 12 inches times, now we know the y, it can be positive or negative, but when we're looking at this rectangular cross section, the compressive and the tensile the stresses will have the same magnitude. So really, we'll be good because the y is the same. So we don't really even have to worry about the sign convention here, because the positive and the negative will be the same magnitude. So we just plug in the 6 inches. And then the I, well, we solved that as 1152. So let's solve that out. That comes out to be 11.5 for KSI. So our closest value is this 11.6. So we're good. So yeah, please let me know if you have any questions on how I did this, and hope you have a great day.